So, can you guys remind me where I left off? Were we talking about weak bonds and strong bonds?
We just got done with covalent bonds.
We're on ionic.
Sodium's big bully.
It is. Actually, it's chlorine that's the bully.
Oh, chlorine's the bully.
Okay, so we talked about electronegativities.
We're on slide 23.
This one.
Yeah.
Okay, so we covered the single bonds and double bonds. Everybody understands that? Okay. And that double bonds are unique because they can't rotate. Single bonds can. Good. All my classes are starting to run into each other. Okay. We talked about valence? No?
Yes.
Yes? Alright, so just make sure that you guys understand that valence is the number of bonds that something can form, an element can form. Valence electrons means how many electrons in its outer shell. So, for example, oxygen has how many electrons in its outer shell? I hear 1, I hear 7, I hear 6. 6 is the correct answer. So its valence electrons is 6. However, it has how many unpaired electrons? 2. So its valence is 2. Get it? So I might ask you on the test, what's the valence of carbon? 4. What's the valence electrons of carbon? Aha. Yeah, so it's one of the only elements that has the same number for both of those. What about hydrogen? What's its valence? What's its valence electrons? Good. So there's another example. Nitrogen is 3. You guys noticed that the nitrogens that you used in the lab had 5 holes. That's because nitrogen sometimes gets confused. So it has 5 electrons in its outer shell, right? Remember, you could lose all 5 or you could gain 3. Sometimes, it forgets it's easier to just get 3 than to lose all 5, and so that's why it can form 5 bonds instead of 3. Does that make sense? Alright, so everybody understand ionic bond? What's that formed by? Transfer of electrons, right? And so it sets up a charge, positive and negative. And then a covalent bond, what's that? Sharing. And there's 2 kinds. One is that they share equally, and what's that called? Nonpolar. And if they don't share equally, then they're polar. So we can predict how these electrons are going to behave, these elements are going to behave, based on something called electronegativity. So everything has a certain electronegativity. You can kind of, equate it to your strengths. So like all people have different strengths, like you could think of mental strengths or physical strengths, whatever. So atoms that have more electrons in their outer shell are going to be stronger. They're more able to keep electrons and get electrons from other people. You kind of think of it as like the bully in the schoolyard that takes your milk money, right? So the bigger and stronger they are, the more apt you are to just like hand it over, right? And so, things that are in the upper right, like fluorine, are big bullies, And I told you guys that fluorine is so good at doing this that once it gets electrons, it will never give them up. It's almost impossible to reverse it. Things over here are real weak. So sodium is real quick to give up its electron, right? And that term, its ability to keep and hold electrons, is called electronegativity. So this is a great marker. I should keep this. So electronegativity is the difference in so it's just a value that's been developed by a chemist, right? And it ranges from 4 to 0. 4 being the strongest, 0 being the weakest. Some examples of electronegativity is carbon's electronegativity is 2.5, hydrogen's is 2.1, fluorine's is 4, oxygen is 3.5, so sodium is 1.0. Right? So we can predict, based on differences in electronegativity, what's going to happen when two elements encounter one another. So let's say that, well, I'll just give you the value. So a covalent bond is something that is generally, and it really depends on what text you read, but generally it's something that that value is bigger than 2.5. All right, so if the electronegativity is 2.6, I'm sorry, not bigger than, less than. So if the electronegativity is 2.6, it'll be ionic. If it's 2.5 or 2.4, 3, 2.3, and so on and so forth, then it'll be covalent. So ionic is generally greater than or equal to So we know that there's two different kinds of covalent. So we have polar and nonpolar. And so for polar means that they don't share equally. Usually that's between 2.5, so less than 2.5, but greater than 0.5. And nonpolar is less than or equal to 0.5. So if there are two atoms that came together and the difference in their electronegativity was 0.4, what kind of bond would they form? Nonpolar what? Covalent, right? So make sure you use nonpolar covalent. What about 2.3? Good. And then what about like 2.6? Good. So let's take some examples. So what about carbon and hydrogen? What bond is that going to make? There's only three options here: polar covalent, nonpolar covalent, ionic. So what's this electronegativity? 2.5. Hydrogen's is 2.1. What's the difference? So what is it? So 0.4 is less than or equal to 0.5. So it's going to be nonpolar. So examples of these are hydrocarbons like fatty acids, oil, things like that. So those sorts of molecules are going to be nonpolar. Make sense? All right. What about water, our good friend water? What kind of bond is that? Okay, so let's check. Oxygen is 3.5, right? So that falls in this range. This falls in that range. So this is a polar bond. Any questions about that? Chlorine is like 3.7. So what's that?
So how do we calculate?
You can't. It's numbers that have been assigned based on experiments done by chemists.
The ones we have to know are fluorine.
You don't have to know any of them. So I'll tell you guys right now. If I ask you the question, I will write it on the test that electronegativities. And in fact, you guys can bring in periodic tables. So if you look, online, like just go to Google and search periodic table and look at images. There are lots of periodic tables that they have the electronegativities printed on them, and you can bring those. So I don't care that you know the electronegativities, but what you do need to know, you'll have to memorize, and I won't tell you, is these rules. So I'll write a bond, and I'll ask you, what kind of bond is that? I want you to predict the bond it's going to form. And I'll give you the electronegativities. You just need to know the rules. Make sense? Okay. So everybody understand nonpolar? And everyone understand polar? And remember, when we have polar, something like water, they don't share equally, right? But they still share. So the electrons, when they're spinning, they spend a lot more time around oxygen than they do around hydrogen. So this sets up that partial charge. We talked a little bit about this, I think. So this, did we? Yeah. Some people weren't here. Well, they were here, but they weren't here. So this is what we use to symbolize a partial charge. It can't be a full charge because that would be a full transfer of an electron. We're not fully transferring an electron, right? It's not like sodium and chlorine. So that's a partial positive charge, partial negative charge. And if you had a glass of water, if the molecules in water interact with each other, you've probably seen this, right? If I pour a little water on this table, is it going to spread out individually by molecules? What does it do? It sticks together. And that's because of this. So another water molecule comes up to this one, and it's going to interact with it. It's going to interact with it in a specific way. So this partial negative charge is going to be attracted to this partial positive charge. It wouldn't turn the other way, because if two hydrogens were together, what would they be? Positive and a positive, and two positives repel. So that would cause this to flip, and now you have this partial attraction, right? It's not a full bond, it's not like an ionic bond, but it's a partial bond, and we call that a H bond or a hydrogen bond.
So does the oxygen molecule go with another water molecule? Does it bond with both the hydrogen molecules over there, or just one of the hydrogen molecules?
So it would just bond with this, and then you'd have another water over here that would bond with that one. And then you'd have another water molecule here, bond here, and another water molecule bond here, where these would be. Let me get another color. So water can form 4 hydrogen bonds per water molecule. So here's our water molecule. There's 1, 2. Here's another water molecule, right? There's a water molecule. And then 3, so there's a water molecule, and then 4. So each of these, let me get another color. This, and that are all hydrogen bonds. They're created by these partial sigma charges. And water interacts that way all the time. In fact, water has an attraction to itself, and we call that cohesion. And we'll talk about that in the next chapter, because the next chapter's title is water. Right, everybody understand that? All right. So this gives water the cohesive properties, but it also makes it a good solvent. In fact, water is considered a universal solvent. And I'll tell you why when we get to chapter 3. Question?
I did. It's probably a really dumb one. So that determines what kind of bond it's going to be with hydrogen, one hydrogen and oxygen.
So they're not really bonds, right? Because this is what water's like. So there's only two bonds in there. These don't form a bond.
Okay.
So this is all we need to predict is the stakes. I mean, there is some interaction with these, but it's not enough to warrant even going down. Like when you take a chemistry class, you can learn, partial sigma charges and different spins on electrons and that sort of stuff. But just for this class, I'm just going to teach you the basics, enough for you to get by to understand what the heck I'm talking about next. And this is really important because you guys know that we all need water to live. Like, can you think of any living thing that can live without water? So the question is, why? Why do we need water? Why can't we live on isopropyl alcohol? Or liquid nitrogen? Or methane? Or can we?
Your body does require alcohol, but a little bit of alcohol.
But I mean, the question is, why do we need water? And we're going to answer that. We're going to talk about that. And these are questions that are relevant because, remember, there's a moon that's, going around Jupiter that has an icy cover on it and a liquid ocean underneath. So, will life exist there? There's another moon that has liquid lakes, but they're not water. They're made out of liquid methane. Will we find life there? Why or why not? Is it worth it to build a $20 billion spaceship to go check out this liquid methane for life? Is it worth it to build a $20 billion spaceship to go to Europa to look for life? So you have to weigh these. I mean, there's scientists at NASA that are hired to do this, astrobiologists, that's their job to figure out. Is it worth it? Are I going to look like a fool? So you got to, and if you don't understand how this works, the chemistry works, you won't be able to answer those questions. All right. So everybody understand ionic bonds? Good. Okay, so this is important. When we're talking about ionic bonds, the root term is an ion. An ion means a charged particle. So when you have sodium and chlorine come together, you know that sodium gives up its electron to chlorine, so that sodium has a full shell, outer shell, and so does chlorine. In the process, sodium gets a charge. What is that charge? If you lose an electron, you have an extra proton, right? So it's positive. Chlorine gets a charge, right? And that charge is negative. So when we write it out, we write out Na plus Cl minus. That's really what it is. And what's holding them together? It's the attraction between the charges, right? We call that an ionic bond. So this, because it's got a positive charge, it's called a cation. So the root cata means down, right? Like catatonic. And we're going to talk about this too when we talk about metabolism. So there's two kinds of metabolism. One is anabolism. You remember what ana means? Remember, it was funny because I was talking to you guys about Hans and Franz or whatever. And I haven't seen that on Saturday Night Live for like 15 years. And then I was watching TV last night and there's a Geico commercial with those dudes on it. It's like, oh my God, that's awesome. So they're making a comeback. So ana means up, right? So if you lose an electron, what happens to your shell? It goes down, right? And if you gain an electron, it goes up. So the word ana and cata are relevant here. So this one is getting bigger because it's gaining electrons. This one's getting smaller because it's losing electrons. All right, and then so, scientists speak in terms like if I want to copy DNA, I need an element that helps the enzyme copy DNA, and that's a divalent metal cation. What does that mean?
A double valent metal cation.
So what's its charge then? Give me an example of a divalent cation. It's okay, you can use the periodic table.
A double valent.
Divalent cation. So it means it has 2 electrons, right? Divalent. So, yeah. So, well, no, helium's not everything that it needs. So, this is a monovalent, right? Has 1 electron. So what's that?
Beryllium.
Right, magnesium, calcium, right, those are divalent cations. So that's, the reason I'm telling you this is because that's how scientists talk. So if you can't understand my language, then you're not going to be able to read stuff or talk to me at a bar, because that's how I talk. Alright, so everybody understand cations and anions? I might ask you, I might put a molecule on there and say this charge is, -2. What is that? Cation or anion? Get it? All right. So in biology, there are bonds that are strong and there are bonds that are weak, and this is really important because you want to be able to respond to your environment. We define that in the very first chapter. That's part of life, right? Respond to the environment. Everyone agreed on that? I was here. I know you did. Do you believe it? We talked a little bit about, if you go outside in the cold, what happens? You shiver, and then if you couldn't respond to your environment and you went back inside, what would happen? You'd keep shivering. So, you would never be able to respond to your environment, and that would be super lame. So it's these bonds, these transient bonds, right? Your DNA makes proteins that, only bind for a little bit. Insulin's a good example, right? Insulin doesn't bind to your cells all the time. It controls whether your blood sugar gets put into your cells or not. What if insulin bound there and you couldn't ever reverse it?
You would be hypoglycemic.
Right, you'd be hypoglycemic. So it's important that sort of bond that insulin makes with the receptor. So if you don't know this, I think we talked a little bit about receptors. So insulin's a molecule. This is an insulin receptor. And insulin has the shape. Shape is really critical in biology. It's the most important thing. That binds there and activates genes that open a channel for glucose to go into the cell. All right? So if this insulin receptor isn't the right shape, what's the result?
It doesn't open.
It won't open, right? So if the insulin receptor isn't the right shape, it wouldn't matter how much insulin you gave the patient, because it would never bind. Does that make sense? Or your insulin could be the wrong shape. And in that case, you could give the patient insulin because assuming that the insulin you give them is the right shape. Make sense? All right. So this is an ionic bond. It's not a covalent bond. What if it was a covalent bond? Covalent bonds are strong. Ionic bonds are weak.
It would attack their state.
Right. And would that be a good thing? Because you couldn't respond to your environment. You couldn't respond to the food that you eat, right? And just like in biology and most things in life, too much of a good thing can be bad, right? Too much sugar in your blood is toxic. Too much oxygen in your system is toxic. So it's important that you're able to maintain a certain level. And you have to be able to, so bonds that are weak are hydrogen bonds, right? They're not even as strong as ionic bonds. Ionic bonds are weak, but not in the presence of water. So I'll give you an example. You guys seen like one of those salt licks that they give to horses or whatever? So how would you feel if I picked that and threw it at your head? It would hurt, right? Because the bonds in there are strong. But what if I soaked it in a bucket of water for a week and then threw it on you? So you know that ionic bonds in the presence of water are weak. What are we mostly made out of? Most of you guys know that. Water, right? We're mostly oxygen as an element, but as a compound, water. So ionic bonds in you, are they strong or weak? Weak. And so ionic bonds are reversible. Hydrogen bonds are reversible. Covalent bonds aren't reversible. They're permanent bonds. And you have to think about this when you're giving medications to patients, right? What if you gave a patient a medication that wasn't reversible? Yeah, I mean, like, what if you're trying to, like, get their heart to go into rhythm by, like, stopping it? You give them a medicine that stops their heart. Would you be able to restart it if it was covalent? What if it was ionic? Yeah. So, this is important. You guys probably seen the commercials for the purple pill, Nexium, Prilosec. So that works. We're going to talk about this in the next chapter. But you guys have a stomach? Well, I know you do. And on the outside of that stomach are cells called parietal cells. There are blood vessels that run along those cells. And those cells' job is to take hydrogen ions, right? I call it an ion because it's has what? It has a charge, right? And this pump, it takes hydrogen ions. If it was hydrogen, I wouldn't write the plus there, right? So it's an ion. It takes hydrogen ions out of your blood and puts it into the lumen, which is the inside of so that's the word of the day, lumen, inside your stomach. This changes the pH because pH stands for power of hydrogen. Really, the word is process because it's French. But that process means power in French. So I just switched the names out. Power of hydrogen. The more hydrogens you add in here makes the pH go down, which really means that the number of H pluses are increasing. And I'll show you why in the next chapter, but just trust me, it is. So this is called a proton pump. Why is it called a proton pump? What is it pumping? What is H plus if we break it down to subatomic particles? How many protons, neutrons, and electrons? It has one proton. If it had two, it would be helium. One proton, one electron, but doesn't have one because it's a H plus. So it's just a proton. So therefore, it's valid to say it's a proton pump because that is what H plus is. Make sense? So Nexium and Prilosec, you take that medicine and it binds right here, and it effectively blocks the proton pump. So what happens then? pH goes up, so the acid goes down, right? And so the whole point of taking that drug is it's an antacid, right? That binds covalently. Really? So if that wasn't reversible, what would happen? Okay, and so you would die. That's right, you would die. So why are people dying left and right from taking this drug? Yes. So this one's specific. It's a specific shape that only binds to this specific proton pump. But that's a good question. So what she said was proton pumps are used to make ATP, which is true. But this drug has a specific shape to this particular proton pump. So it doesn't affect your ATP production. That would be really bad, right? That would only take a couple minutes and people would be dying right away. So, 10 minutes, you're dead. They might use that in California to execute people, you know. Mm-mm.
Because the proton pump is constant in the medicine, they take it, and then it's gone.
No, it still binds to the cells. It doesn't go away. It's a covalent bond. It's not reversible.
It binds to what cell?
The parietal cells that line your stomach.
Those cells have a short life.
That's right. That's exactly right. So, some of your cells are never replaced, right? Like, you guys know this. If you sever your spinal cord, those are nerve cells. Do they grow back? No. So, some cells are never replaced. But cells that, like your skin cells, they're always being replaced. And it turns out that the cells that line your digestive system are always being replaced too. So, this drug is fine to give for this reason because cell will die and a new cell will take its place that won't have that drug on it. But you wouldn't want to use this in a heart because what would happen then? The cells would die and they would never be replaced, and that would be bad. So you have to think about this when you're given medication. What's going to happen when I give this to the patient? You know, a lot of you guys may go into not medicine but like research, and so you may end up developing these drugs. You have to think about that when you're doing clinical trials on people, how it's going to interact.
So what's the shelf life of those cells?
You know, maybe a day. You know, I'm not sure exactly.
Is that why they
24,
say
48.
cells only work for 24 hours, like Riley said? The cells die within
I'm
24
sure,
hours.
yeah, they've replaced the cells. So there's other things, right? Like, you know, things that are found in nature that affect the proton pumps in the electron transport chain that make ATP. Two of those things are carbon monoxide. Well, that's just one. Carbon monoxide and cyanide. So cyanide binds covalently and shuts down the proton pumps. Carbon monoxide binds ionically to shut down the proton pumps. So which one of those is reversible? If you had cyanide poisoning and you went into the hospital, there's nothing you can do, right? There's nothing they can do for you because that. So cyanide is covalent. Carbon monoxide is ionic. So you get cyanide poisoning, you're done. You can't reverse it. Carbon monoxide, you can reverse it, right? So, and it binds at the exact same place. That's the main difference between these bonds. So really in biology you got to think about, is that permanent or temporary? Your DNA is like a book, right? So it has two strands. You guys know that from the first chapter. In order to read the DNA to make your, to make your recipes, you have to open the book. So would you want your DNA to be held together with covalent bonds? If it was, it would be like me going, hey, go photocopy this textbook, but I super glued all the pages together. What are you can't open it, right? So hydrogen bonds hold your DNA together so that you can open it and read it.
So like a snake bite, like, rattlesnake bite, you end up having to cut off part of it. Is that considered covalent because you can't reverse it?
So those are proteins, right? And you could reverse them. There's a couple things that will change the shape of proteins. Temperature will. So will changes in pH. But those are complicated, right? They contain all kinds of bonds in them. We're going to talk about that when we get to functional groups in chapter 4 and 5. But, even electricity can, so like if you get bit by a snake, you can shock the crap out of yourself and in the hopes that it will change the shape of the venom protein so that it won't be toxic. It's like a taser. I'm not sure how well it works or if what kind of damage you're doing to your own cells.
Just don't tourniquet your arm.
Yeah, I mean, it really depends on how the snake bites you too, because I have friends that keep venomous snakes. In fact, the department chair Andy Baldwin is a snake freak, and so that's kind of how we bonded when he first got hired. He got hired after me, and so I had a friend that got bit by an Egyptian cobra, and the fang went through his blood vessel to the other side, and so it just envenomated his muscle, so he was fine. And then I had another friend that got bit right directly in his vein, so the venom got released and he died. He didn't make it out of his garage into his house, and he had anti-venom. So it really depends on if it's injected into your bloodstream or into your muscle as to how fast it's going to affect you.
See the video of what drop of venom into the blood, spill out the blood for the slime.
Yeah, so there's two different kinds of toxins. One is a hemotoxin that will break down your blood vessels, your blood, and that's, rattlesnakes have that. And then there's a neurotoxin, which
Paralyzes.
cobras and things like that have neurotoxins, and what it does is it affects your ability to breathe and your heart to function. I'm not sure. I mean, I imagine there probably different kinds of scorpions have different toxins, just like snakes. But I don't know enough about
There's a snake.
scorpions to answer that.
There's a snake in Africa that bites you.
I got a 50-50 shot at guessing it.
Makes you bleed out all your vessels. What kind of venom would that be?
I would say that that's probably a hemotoxin because that would affect your blood, not your nerves.
But it's like, so hemotoxin.
Some snakes have a mixture of both, So, but yeah, there's different kinds of toxins.
Just kill all the snakes.
Then you'd have a rat problem, and then that would affect. Then you'd have a bubonic plague problem. So it's a nasty cycle. All right, so yeah, don't play with the poisonous snakes. Hydrogen bonds. So you guys understand that, and that they're weak. They're about 1/20th the strength of covalent bonds. They're important in biological systems, and we'll talk about that. They allow for transients, but they also help water be attracted to itself. So we call that cohesion, and that results in surface tension. You've probably seen like insects walking on water. They're not really magicians or anything like that. They're taking advantage of water being attracted to itself. So you can kind of think about it as, you've seen people do stage dives and stuff like that, and generally that's other people were holding hands to catch them. But what if those bonds were weak? Like people were just barely holding on to each other's hands. Yeah, and it's the same thing with the bug, right? So if you put that bug on something that didn't have hydrogen bonds, like alcohol, they would just sink because there's nothing to hold them up. So on a molecular level, this creates surface tension, and so that's why certain things can. Like there's a lizard called the basilisk that can walk on water because it has big feet and it has a lot of surface area. You could walk on water too. You just have to run about 150 miles an hour.
Don't they call it
Yeah. All right, and this will be important too when we're measuring stuff. But we'll revisit this again in the next chapter. Everybody understand electronegativity and how to calculate that? All right. So electronegativity is really important because really what's going on with life is that we're moving electrons, and I told you guys this. When you eat food, you're moving the electrons off of carbon onto the oxygen you breathe. Which one's more electronegative, carbon or oxygen? You can look at the table, which one has more electrons in its outer shell. So then oxygen's going to be better at getting the electrons from carbon. That's the natural flow of things. Plants take the electrons off oxygen, off water, and put that onto carbon. Is that the natural flow of things? is it normal for carbon to take electrons from oxygen? No, because it has a lower electronegativity. So it's not as strong. So it's just like water, right? If I'm on a hill and I pour water out, where's the water go? Up? Down, right? If you're at the bottom of the hill and you pour water, would you expect it to go uphill? No, because that's not how things work. So, but could you get it to go uphill? Pump. And so what, how do you get a pump to work? And so you have to put in energy, right? So plants take electrons from oxygen and put it on carbon, just like they were pumping water uphill. So where do they get the energy to do that? From the sun. That's exactly right. And if you didn't release energy, if it wasn't normal for you to eat food and release free energy, what would be the point of eating if you had to put energy in to get your food out? There wouldn't be one, right? So that's how things work. And we're going to talk about how it moves against the gradient from oxygen to carbon when we talk about photosynthesis, and then we're going to talk about how it goes with the gradient when we do chapter 9, respiration, which is what you guys do when you eat your food and break it down. All right. And everybody knows that different things have different affinity for electrons. So if I gave you a metal fork and a plastic one and said shove in the outlet, yeah, I think you get it. So we're going to talk about that because we have to get electrons to flow to make stuff work. Okay, so the next thing we need to talk about is chemical reactions. We write out chemical reactions using parts, right? So, I use this example all the time. It's basically, if you want to build something like a car, you have parts. And if you have odd number of parts, then you're not going to get a whole car built. So you have to have a specific, whatever you put in comes out in the car, right? There's not some magical tire fairy in there that puts extra tires on it. They don't create it out of nothing. It's just like Legos. So chemicals are just parts. Elements are just parts. And we can't violate the laws of physics and create or destroy these things. They can only recombine in different forms, kind of like a transformer. So hydrogen, that never exists by itself. Why? Why is it always H2?
It's 2 hydrogen.
Okay, well why? Now I'm going to be like my 5-year-old. Why?
As a missing electron.
Right, so by itself, it wouldn't be happy. It needs to have its outer shell full, so it will always seek out another hydrogen to make H2. This is, it always exists like this with a single bond, remember? Oxygen is always O2, why? Right, so it doesn't have its outer shell full by itself, so it will quickly find another oxygen. How many bonds between two oxygens? 2, good. So all we're doing is, just like you guys did in lab, you're just taking these apart and rearranging them into a new shape. Really simple. So if we combine hydrogen and oxygen, we get water. Do I get to see that? So this we call reactants, and this is the product, but there can be more than one, so they could be products. Do the parts match what goes in and comes out? Do we use all the parts? We can't do that. We have to make sure that both sides are equal with each other. Whatever parts we put in have to come out the other side. So what do we have to do to fix this? So we can we can put numbers in front of this, no problem. I can put a 2 there, because I'll make 2 molecules of water instead of 1. Just like, if I have 8 tires, I can make 2 cars out of that. Assuming we're talking about a car with 4 tires.
But if you want to use both oxygens, then you have to make oxygen too.
So let's start here. Let's just figure out like what we have. So I'm going to erase this. How many hydrogens do we have?
2.
How many oxygens?
2.
On this side, how many hydrogens?
2.
That's fine, right? They're equal. How many oxygens?
1.
That's a problem. So I can't reduce this. I can't cut that oxygen in half. But I can increase the number of waters that I make. So what do I have now?
4 hydrogens. And 2 oxygens.
Now the oxygens are balanced, but the hydrogens are messed up. So what do I do now? I go to the other side and I can put a 2 here, and now I have 4 hydrogens and 2 oxygens. That equation is balanced. Everybody get it? All right, let's try a harder one. What do you guys do to make energy? What's the chemical reaction, do you know? So what do you need to live? Oh, so where do you get your energy? From the sun? From dirt? From electricity? Stick your finger in the outlet? So you guys know that you breathe oxygen. You need that to live. What else? So you need water, but that you get that from external sources. You don't make it. So food. This is glucose, in case you don't know. You'll learn that before the semester's out. Huh? Right, so this could be anything, this could be fats or whatever, but essentially they get converted in this, and I don't want to get into any complex reaction. Let's just keep it simple. You breathe air, you eat food, you make energy. That energy is in the form of ATP, but that's made by taking ADP, which is a diphosphate, and adding a phosphate to it. And you guys may have done that in the lab with the molecules. You probably just were like, I've had enough building molecules and left. And you didn't go and look at the ones up in the front of the room, but it was there. And so we're not creating anything. This isn't really part of the equation because these get recycled. And then we produce water as a byproduct, and then you exhale carbon dioxide. So is this equation balanced? What are the reactants? Right, so these are the reactants. And these are the products. Is this balanced? What's the problem? All right, let's go through it. So carbon, hydrogen, oxygen. How many carbons? 6. How many hydrogens? How many oxygens? Good. On this side, carbon, hydrogen, oxygen. How many carbons? 1. How many hydrogens?
2.
How many oxygens?
3.
All right, so that's not balanced at all. So what do we got to do?
5 carbons.
Okay, so do I put a 5 here?
No, because that would be the
Yeah, because you picked oxygen too.
So if I put a 5 there, how many carbons do we get? 5. How many do we need? So I have to put a, good. Now I get 6 carbons, but that changes the oxygens because I can't separate this. Because it wouldn't be carbon dioxide anymore. So how many oxygens do I have now? 12 plus 1 is 13. Same hydrogen, so we're okay there. So now we got the carbons balanced. Now we got to do the hydrogen. So how do we do that? Okay, so how do I So I put a 6 here, and that gives us 12. So now the hydrogens are balanced. But what's going on with the oxygen? Now I have 6 plus, that's 12 plus 6 is, yeah. So that's messed up. Now I got not enough here, so I know I'm gonna have to add some over here. So what do I need to do to make this equal 18? So I put a 9 there. What does that do? That makes 18 plus.
It's 24, but if you put 6, it's gonna be
12 plus 6, and that's a balanced equation. So on the test, I will write an equation out, and I will expect you guys to balance it. It won't be this complicated. It'll be relatively simple, more like the other one. So, like I said, if you're having a hard time with this, you don't get it, you should get that book, Chemistry for Biology Students, or you can also, do a Google search. I'm sure if you put in practice problems balancing chemical equations, you'll probably get a million different sites that can help you practice this. But, the only way you're going to get good at this is just keep doing it over and over again. But there will be a question on a test about this.
Maybe you explain, but why is it important to balance the equation? I mean, I don't get it. Why do you put 6 carbons and, I don't get why you need to balance it.
Because whatever goes in has to come out. It's the laws of chemistry, and it's the law of thermodynamics.
So you're adding more to this side to get all of it out.
Right. You have to balance the parts. It's just a fundamental law of nature. If I give you X number of Lego blocks, you have to use all the Lego blocks of what you're building. You can't only use half of them. That's against the law of nature. It's against the law of thermodynamics. You can't. Once a reaction occurs, it has to go to completion. You can't stop halfway through. Does that make sense? So it's not a valid chemical equation unless it's whatever goes in has to come out. And you can't have extra junk come out of nowhere, because you can't create matter or destroy it. Yeah. So we'll talk about this when we get to chapter 8. Yeah, which is metabolism, because that's a really important concept. These pesky laws of thermodynamics that physicists hate, because that means they can't travel in time. We'll talk about that when we get there. But you guys know Stephen Hawking. So he buried a bunch of invitations in the dirt at various places around the earth, and it said, "Come to my time travel party. It's going to be on this date," or whatever, thinking that, if in the future time travel was possible, somebody would unearth this and come back in time and, say, "Hey, what's up, Steven? I got your invitation to your time travel party," or whatever. But when the day came, guess what? Nobody showed up. So what does that tell you? Right. So, Stephen Hawking is this brilliant physicist, but I could have saved him the trouble, because I know that the law of thermodynamics is the most tried and true law on the planet. It's been tested more than any other law. And so what it says is that every time we do a chemical reaction or a change of energy, then things go towards disorder, right? Disorder means, as we get older, we break down. Your car doesn't improve as you drive it. The pyramids don't get more shiny as time goes on. So if you were in your kitchen and you knocked an egg on the floor, what would happen to the egg? It would fall and break. So that ordered egg would become disordered. So if you traveled backwards in time, what would have to happen to that egg? And so that would mean it would go from disorder to, and that violates the law of thermodynamics. So bam, you can't travel in time because you're violating the law of thermodynamics. So just a little physics lesson there. All right, everybody can identify reactants and products. If I throw this equation on there, you know which one is which. All right, so chemical reactions can be reversed and they can also go to equilibrium. So this is what we do, but guess what if you were a plant and you were doing photosynthesis? This arrow would become this. This would be energy from sunlight that would have to go in. That works fine. Because we have to move the electrons, right? From oxygen to carbon, and that goes against the gradient. And so this would now become the reactants, and this would become products, right? So if this sunlight is required to drive, like sunlight is energy, right? So we don't have to add them as matter because that's what this is. Energy isn't matter. If sunlight drives this reaction, and this is what plants use for energy, what would happen when the sun set? What happens if you don't have energy? You would die. So how come when you wake up in the morning your trees and bushes are still around? They store energy in the form of So where do you get your energy from if you're eating a bag of Doritos? Carbohydrates, right? Well, this is a carbohydrate. So what plants do is at night they switch. They do what you do. They breathe oxygen. They use the stored sugars that they made during the day, and they produce energy the same way you do. So at some point when the sun's setting, sunlight gets lower, they can't make energy this way. They reverse the reaction, and so the rate of these reactions are equal, right? They're producing sugar at the same rate they're breaking it down. And that's what we call equilibrium.
So if you have a plant here, like bulbs, if you have a light on them all the time, is that actually unhealthy?
I don't think so. I don't think it would care, because it's just going to keep reacting. So you would have rate limiting steps, right? Because we're going to do an experiment in the lab, and you'll see the effects of sunlight that has on plants. So it's not the amount of exposure, but the intensity of light that will affect it. Yeah, so we'll answer that when we're doing the photosynthesis lab. All right, so everybody understand chemical equilibrium? It's simply defined as the rate of the production of the products equals the rate of the formation of the reactants. Or in other words, the reaction is going at the same rate in both directions. All right, any questions about any of that? All right, we're done with chapter 2, so we're going to go to chapter.
I have a question.
Yep.
But if it's growing at the same rate, then it would be no glucose left.
No, the rate that it's being formed is the same rate it's being broken down. It would be like if you had an iPhone and you were disassembling it and someone over here was reassembling it at the same rate. So you would end up at the same point. You would just be building it and breaking it down, building it, breaking it down.
Find the plants.
The what?
Then when the plants grow,
Mm-hmm.
have the fiber that we use to eat.
Right, so this doesn't happen all the time, right? This is only when there's certain light levels. Does that make sense? You'll see when we do the experiment. When the light gets low, the plants are forced to use their stored energy to live. right? So only when it's about to get dark or right after the sun rises do they do this. Not always. Most of the time, it's going that way. They're making sugars.
So is that why they would eventually die without sunlight, because they've used up all the glucose that they've stored?
Yeah, they would. Yeah, if they didn't have sunlight, they couldn't make glucose. They would just like you guys, right? But you don't store your energy as glucose. What do you store your energy as? Fat, right? So it's the same thing. Plants store, and the reason is because this is real easy to store, right? Fats take a little bit of processing to make, but they have more energy per weight per gram. So this has 4 calories per gram. Fat has 9. So if you stored your energy as carbohydrates, you would weigh a lot more, and that would impede you if you were getting chased by, a lion or a tiger or something like that. Plants, they don't care, right? They don't have to run anywhere. It's not like, oh no, there's a lion, I better get out of here. I'm sorry that I stored all my energy as carbohydrates because that will slow me down. They don't do that. So there's reasons for that. Okay, so this chapter is on water, and it kind of addresses the point of like why we live off of water, and what's the effects of water on pH and stuff like that. Okay, so that should come on. So water is the only substance, chemical compound that can exist in all 3 forms on Earth simultaneously. So it can exist as a solid, what do we call that? Ice, and then a liquid, and then gas, which is, would you tell me it was, Mohammed, what was it in here? Yeah, so humidity is water in a gas form. So all 3 of those, solid, liquid, and gas, no other substance on Earth exists we're not talking about in a lab, right? We're talking about in nature. So you guys understand hydrogen bonds? And we talked about the maximum number of hydrogen bonds that water can form is 4. Good. So, it was playing and I stopped it. Oh, there we go. So molecules move, right? And then it went away. So molecules move, right? When we heat molecules up, what do? They move faster, right? We cool them down, they move slower. So, imagine I'm a water molecule and I have 4 hands, or 4 arms. So I'm holding on to 4 other people. And as, I heat them up, they start jumping around and, they're harder to hold on to, they're harder to control. When it gets cooler, they slow down and they stop moving. So it's much easier for me to form 4 hydrogen bonds, right? If it's hot, I may lose a couple people. They may break my bonds, and then, I'm going to be grabbing for other people that are running around the room because I want to form bonds. So in liquid water, these bonds form transiently, right? They break, they form, they break again, and so on and so forth. In ice, the bonds are rigid, so there it went. So you can see in liquid water that it's moving, right? In ice, it stays the same, and you can't see this, but it actually literally spreads out the molecules by increasing the number of hydrogen bonds that are permanently formed. So you know this. If you went home tonight and took a bottle of water and put it in your freezer, the next day when you took it out, what happened? Some leprechauns went in there and made it bigger. Why does it expand? The hydrogen bonds cause it to spread out, and that causes something unique. There's a term that we use called density, which is the mass per volume. So that water still has the same mass. If you weighed it before you froze it and weighed it after you took it out of the freezer, it would weigh the same. But it takes up more space. That means it's less dense. And you know this. So if you took that frozen water and put it in a lake, would it sink? It floats. So that means that ice is less dense than liquid water. So that is unique. Most things, when they get colder, they get more dense. And you know probably from swimming that if you swim in a lake and you swim down, what happens to the temperature of the water? It gets colder. But water's weird because it will get more dense until it hits 4 degrees, and then the hydrogen bonds start locking in, and then it gets less dense. So how do lakes freeze? On the bottom up or from the top down? And all water does that. And that's important because ice is a good insulator. So, think about it this way. You've probably seen like Bear Grylls shows and stuff where they're stuck out in a snowstorm and there's no trees or nothing around. What is the first thing they do? Yeah, so they either build an igloo or dig, a snow cave or whatever. That doesn't make any sense, right? It's counterintuitive, but really, it's a good insulator. And it's the same thing's true for lakes. So if during the last ice age, water didn't freeze from the top down, there would only be like an inch of water on the oceans right now. So there wouldn't be very much water at all. Why is there so much water? Because it froze on the top and insulated the water underneath. So that means that if we found this planet Europa that has even 100 feet, 100 miles of ice on top, there's a good chance that underneath it there's liquid water, right? Because that's how water works.
How do we know that it's water? What if it's like the same thing as what's on?
Well, I can tell you, and you will learn this in chemistry, that when you put energy into certain elements, they reflect certain wavelengths of light, and so that you can detect signatures of different compounds based on their pattern of reflectiveness of light. So you could tell by shooting a laser at it and detecting its range that the elements repeat the signal back because of the electron configuration what it is. So I can tell you that they know that there's water there. And when I used to work at a water consulting firm called Aquatic Consulting and Testing, which I think I told you guys, but we have to test water all the time, right? So there's a dude that came in who was convinced that the government was conspiring against him, and they were putting fluorine in his water, and it was ruining his life and causing him to be mental and all this stuff. And he would bring all kinds of stuff in, right? Soda, bottled water, and all this stuff, and we would have to test it. And the way we did that was we would shoot a laser into the water, whatever he brought in that day, and it would send a signal back. Most of the time there was no fluorine in it, but this dude spent thousands of dollars bringing this stuff in to test it.
You worked with Dr. Maltby.
I don't know who.
Rick?
Rick. I don't remember. We'll have to talk later because I haven't been there since 1998, so I don't know who's there anymore. Is he the head guy? Yeah, okay. Like San Diego, mustache. Yeah, I know. So there's a woman that owns it, right? And then he's the PhD scientist that runs it. And then there was another guy who's a QC guy, which I think he left. They kind of have a big turnover, so I don't know who's there anymore. But yeah, I worked there. Yeah, I remember talking to him about he wanted to go to the World Series in San Diego and that's the last year I worked there. So I don't even remember what year that was. But all right, enough about my life. So cohesion is water's attractiveness to itself, and we talked about that. And then there's another, so because of cohesion, plants are able to live. You guys have a circulatory system. So when you want to move nutrients around your body, what's responsible for doing that? Right, your blood, right? Because your blood carries your nutrients and oxygen and stuff like that. But and what pumps your blood? Your heart. Do plants have a heart? So how do they circulate their nutrients? Through their body. So do the roots pump water? So how would it move up to the leaves? Well, I mean, at some point it's going to get saturated. If I took a paper towel and stuck it in water, it's going to stop absorbing water at some point, right? Right? Everyone agree? So how does water get up to the leaves? And the answer is, it does that through cohesion. So the leaves evaporate, water goes into vapor, right? Once that leaves the leaf, it's pulling on the water that's in the roots. Right? So it's like a string of water molecules that pull it up. So that's how plants circulate their nutrients, through cohesion, right? From the roots to the leaves. And then there's another property called adhesion, and that's water's attractiveness to not itself, but other things. And you guys probably saw that when we did the first lab, that meniscus, where the water gets pulled up on the sides of the glass. That's because water is attracted to glass. Right? And so, you can do this magic trick with, people that are younger. They think it's fantastic. But if you take a cork, right, you put it in a glass, because the water's higher on the edges, where's the cork want to go? So if you had cork on a wave, where would it go? It goes to the highest point, right? So if you put a cork in a glass and the water's higher on the edges, where does the cork go? To the side, right? And then when you fill it up, it attracts it to make it, bend down, so it's concave. And so then where's the highest point of the water? In the middle. So the cork will move. Once you fill the glass up, it'll drift to the middle, right? And like 5-year-olds are like, wow, like a magician. We call that thing a meniscus, right? And when you're measuring stuff, you want to measure from the bottom of the meniscus, not from the edges. Same thing if you're pulling a syringe, because if you don't do that, if you measure from the edges and not from the bottom, then what's happening to your patient? You're not giving them enough medicine. Does that make sense? Alright, well, we'll just pick this up Thursday. Alright, so now I'm intrigued. How do you know?
Oh, because I manage a property that has a lake, and so I've worked with him for years. And I've worked with
Okay, so
him.
you have to submit samples.
Yeah.
Yeah.
Well, they came out about it too, but I've talked to him for years. He's really intelligent, kind of odd.
I never really interacted with him because I was in the lab and he was in his office.
Okay. Yeah.
So I don't really know him that well. Like I probably had said 20 words to him.
Well, it's funny because I actually got really angry about my job one day, and I asked him, long story, I asked him, I said, can I come work for you? This is what I'm going to school for. I said, can I come work for you? And he laughed. He said he'd be overqualified at that point. But, he said,
Yeah,
sure.
there's not much to it.
Yeah,
Like,
no, I
you know, it's kind of, it's like repetitive lame stuff, you know, like put the sample in, push the button, read the results, or you know, you want to find out if there's like organic material in it, so you put in like some bacteria. If they grow, you know that it has. So you test the oxygen. So
Right.
all day you're okay. That oxygen level's 7. That you know, and it's just you would hate it. It's really monotonous. It makes a lot of money, but it's very